Hello everybody, my name is Kamau Kingora. Welcome to my talk. Today I'm gonna be talking to you about the numerical simulation of mass transfer over multiple cylinders. The presentation is divided into a few categories. First, we are gonna have the motivation and the introduction. Secondly, we are gonna have the numerical methods, the convergence study and validation of the same. And then finally, we are going to be having the results section, which is actually divided into three sections. That is the result for isolated cylinder in closed flow, side-by-side cylinder in closed flow, and finally, a group of inline cylinder in closed flow. Finally, we are going to be having, stop with the section. We have to ask ourselves, why do we need this kind of study? So there are various engineering applications that can be modeled as a group of cylinder in closed flow. One of them is actually the suspension bridge, the infamous Tacoma bridge. Then we have the marine risers, the closed flow heat exchangers, cooling towers, among others. So there are various studies in literature on two side-by-side and inline cylinders, most of them focusing for a particular number of cylinders. What is the effect of changing the gap ratio, the distance between the cylinders? What is the effect of actually changing the Reynolds number? But very few studies actually focus on what happens if you increase the number of cylinders for a particular gap ratio and particular Reynolds number. Even more fewer studies actually focus on heat and mass transfer characteristic of a group of cylinders in closed flow, either inline or side-by-side cylinders. So in this study, we are going to be focusing on what is the effect of an additional cylinder on a configuration, on an existing configuration of a particular gap ratio and a particular Reynolds number. So that is actually what we are going to be talking about today. This study is a numerical study, and it is carried out using an immersed boundary method. And as you can see in this figure, immersed boundary, we have a Cartesian grid, then we have a shape of the object, and we just map that on the Cartesian grid and impose the boundary condition on the immersed boundaries without actually having to reshape the grid in the computational domain to conform to the shape of the boundary. So there are various attractive immersed boundary method in literature. One of them is we are going to only be focusing on the sharp interface kind. They are actually the diffuse interface kind. We are not going to be focusing on that because they have a limitation of Reynolds number, as well as having not capturing the interface very accurately. So in this study, we are just going to be focusing on the sharp interface method. And there are two famous ones. One is the ghost cell method, and the other one is the part cell method. So the ghost cell method work by use of a ghost cell. A ghost cell is actually defined as a cell in the solid domain that has at least one neighbor in the fluid domain, and that the conservative properties of that ghost cell are modified so that we have the boundary condition imposed at the correct position in the interface. The main shortcoming of this method is that it depends on interpolation. The accuracy depends on the interpolation, and interpolation is not really well posed for a cell with the hybrid immersed boundary and the shaping of the cell near the from one boundary near to the accuracy of interpolation also little. For this, so that is actually one of the major shortcomings of the boundary. And then the other thing is that implementing Newman boundary condition is very tricky. The reason being that not every boundary cell has very easy to treat. So you find that the boundary condition is not captured in a very it kicks off by marking the domain. So the difference domains that are, so if we look at cut cell method, this method is very accurate. Is actually the most accurate immersed boundary method we have today. Have the fluid cells, but it also have shortcomings because it works by reshaping the shape of the boundary cell to conform to the shape of the immersed boundary. But now the problem is cell that is very actually occupied by more than one implement because there are very many cell configuration that can happen from that. In fact, if we have a ghost cell, 108 different cell configuration in 3D with all the cells that are in the solid domain. So, but programming that one neighbor which is the fluid domain of the marking of this ghost cell. So we don't actually have a 3D one ghost cell here and another ghost cell here, and actually also have another one. The other problem with this method is that actually it has very severe time step restriction because the cutting process results in after we get the ghost cell to satisfy the CFL conditions actually mirrored across the immersed boundary. So our aim is actually to come up with an new immersed boundary method that combines the ghost cell method and the properties of the image in a fashion that actually determined by interpolation. And then after that, the property of the image point are used in the ghost cell to implement the boundary condition. So the property of the image point are actually mirrored back to the ghost cell, which is where the virtual forces are to implement the boundary condition. So that is how it works. But now the challenges are that this method relies on the interpolation. So the interpolation, accuracy of the interpolation at the image point determines the overall accuracy of the method. And that is not so good, especially when it comes to cells with higher aspect ratio. The other thing is that the method can be discontinuous from one immersed boundary cell to another. For instance, if you take this cell, you find that we have a position where we have a boundary cell, but we don't have a corresponding ghost cell. So it becomes it actually captures the immersed boundary as a discontinuous kind of immersed boundary. So that is not undesirable, especially when you have kind of human boundary conditions to implement and that kind of a thing. Finally, we have interdependency. Between ghost cells. Like you can find that the interpolation has been used to determine the property at this ghost cell, and then interpolation will also be used to determine the interpolation in this ghost cell, and the dependence within them can actually cause a lot of accuracy issues. So that is the ghost cell. So what do we do to the ghost cell to make sure that we don't have those shortcomings? So we have the domain marking, like in the ghost cell, we have the fluid cells and we have the solid cells. But now we form a virtual ghost cell. Now a virtual ghost cell for all the cells that are in either solid or fluid domain and are actually occupied by more than one phase are marked as immersed boundary cells. So that is the first step we do. And then secondly, we mirror the boundary cell across to the next to the opposite face and form an image point there. So as you can see there. So finally, the property of the finally we construct a virtual cell across around the image point where the boundary, the virtual forces will actually impose the mark, so the boundary conditions. All right. The scores is that we have actually avoided interpolation because the center of this cell is actually the center of the virtual ghost cell corresponds to the center of the immersed boundary cell. So we actually have eliminated interpolation because we already know the values of conservative property at the immersed boundary cell. Secondly, the boundary is represented in a continuous fashion because every boundary cell has a corresponding virtual ghost cell. So in that fashion, we have actually eliminated the discontinuity that was happening in the ghost cell method. So let's dive into the CAT cell treatment of this. And in the CAT cell treatment, we split the boundary cell into various phases such that every boundary cell is now occupied by only one phase. And this is done by actually splitting the cell along the boundary. Like in this cell, you find that we have a plane that actually cut this cell to separate the lower part, which is in the solid, from the upper part, which is in the fluid domain. And that happens for all the boundary cells, as you can see in this diagram. Secondly, we have the cell merging because we have some small cells emanating. Like in this case, we have the gray solid cell that is actually smaller, and that cell, if we treat it, we will need a very severe time. We will suffer a very severe time step restriction. So we need to merge it. We merge it with actually the neighboring cell that is in the same phase as itself to form a one big cell, which actually eliminate the time step restriction in entirety. So that is actually it for the merging process. So we have instead of two different cells, we have one big cells, and that actually eliminate the time step restriction. And the cause of this is that IB coincide with the shape of the immersed boundary. So we have this plane which actually approximate the immersed boundary quite well. So the accuracy of the method is actually very nice, and it also makes sure that the boundary conditions are imposed continuously. If you take the area of the immersed boundary and the area of the planes, they are very, very close, which means the accuracy of this method. order of convergence of this study. So to investigate the order of convergence, we have two cases. The first case, we are going to take the plate and put it in a cavity and oscillate it. Oscillate it. So we will use three three meshes, and these three meshes are systematically defined, and then we are going to calculate the error in each mesh, and we are going to see how does the error behave as we refine the mesh. And after we do that, we actually come up with this figure, which is the order of convergence versus the time. And we can see that at all time, the velocity nx and n, the velocity u and the velocity v are converging with second order. Both of them are converging with second order. So we can say that for a flat plate, the method actually converges with a flat order. One thing that goes without saying is that our method is actually capable of simulating massless immersed boundary like a flat plate, which cannot be said for either ghost cell or the cut cell method. The second one, we want to evaluate the order of accuracy for simulating 3D structures like a sphere. So for this one, we have a sphere oscillating in a cavity, and we test the order of convergence in the same case as the previous case, and we find that the order of accuracy or the order of convergence for all the velocities, that is the u, v, and w, are actually second order with time. The second order in space, I mean. So having found the thing is, we want to validate for the to check the suitability of this method in solving flow with multiple immersed boundary. And for this, we take three side-by-side cylinders at the gap ratio of 4, similar to the setting of a PIV result published by Soraj in 2019. And we want to measure the velocity profile and see whether we compare well with the velocity profile that was published by Soraj. So we take it at Reynolds number 90, and we take the time average velocity for diameters downstream of the structure, and we find that actually the profile predicted by our numerical scheme matches pretty well with the profile predicted by the PIV results. So we can say for sure that our method is capable of solving flow with multiple immersed boundaries. We want to validate the suitability of this method in solving flow with heat and mass transfer. And we have very limited studies with mass transfer, but fortunately for us, that the mechanism of mass transfer and and forced convection are pretty much the same, because both of them are passive scalars. So forced convection and mass transfer are both passive scalars. So we take the forced convection over an isothermal plate, and this was performed by Eckert in 1952 for various Reynolds number, and we compare the profile of Nusselt number along the side of along the surface of the cylinder with the profile that was actually published. And again, we find that we have a perfect agreement between the current numerical scheme and the experiment of Eckert in 1950. So we can actually say that the method is capable of solving flow with heat and mass transfer. Having said that, now let's actually dive into the results section. Now, in the results section, the first section, we are going to cover isolated cylinder in closed flow, and the reason for doing this is that we want to compare the flow structure and the heat and mass transfer characteristic for this single cylinder to the cylinders to multiple cylinder, either inline or side by side. And we can see that we have the vertical structures, and this is lambda 2. The lambda 2 will help us to, the lambda 2 actually depicts which part of the flow is in saturation and which part is in the shear flow. And this one adjusts the Reynolds shear stresses. They actually predict the shear stresses in the flow. And we can see both upper and the lower side of the structure, they have zero interaction in shear stress, which is something that we are going to come to discuss later. So if we check the profile of pressure along the surface of the cylinder, we find that we have very good agreement with the published numerical and experimental result. Hamann in 1936 actually carried out the experimental investigation in a water tunnel at Reynolds number 107, and his result is actually in good agreement with ours, which is at Reynolds number, but the Reynolds number difference is not that significant. We also have the numerical simulation at Reynolds number 100 by Rajin in 2009, and we find that actually the profile he predicted is also in good agreement with our own. But we find normal flow structures, periodic vortex shading. We find the shear dominated zones, and we find the shear dominated zone and soil dominated zones, and the normal flow structures like the needle stresses and so on and so forth. It for the flow characteristic. So if we look at the mass transfer characteristic, we find that we have the scalar being transported and convected downstream, similar to the vortices. And we have a region of high concentration if you look at the time average, and we find that the Choud number along the surface of cylinder is pretty symmetrical. And actually at the region where we have the boundary between the swirling flow and the shearing flow, we have a point of inflection. So we have these two inflection points on either side, which is actually what we expect. Finally, let's go to the side-by-side cylinders in cross. Side-by-side cylinders in closed flow. First, let's examine what happens when the gap ratio is very, very small and we just increase the number of cylinders. So for this one, we are going to have a gap ratio of 1.05. So the difference between the center to center distance between the cylinder is 1.05 diameters. And for that one, we simulate 2, 3, and 4, 2, 3, 4, and 5 cylinders. And we can see that the flow structure, they really behave like a single body, and there is really not much difference as you increase the number of cylinders. There is really not much difference as you increase the number of cylinders. Then we are going to increase the gap ratio to about 1.5 in what we call asymmetrical biased flow regime. And we find now there is actually, so every cylinder is behaving pretty independently. It is not really a single body, but there is a very huge interaction between the cylinders. And we find that there is actually a deflection. There is a deflection of the weight. All along there is a deflection of the weight towards one side or the other. So that is actually a symmetrical based flow regime. And then if we look at the symmetrically based flow regime, we find that we have the wake that is deflected almost equally, in both sides. And that is actually true as you increase the number of cylinders in the configuration. Finally, if you put a very high gap ratio, like the gap ratio of 4, we find that the cylinders behave pretty independently. There is really minimal interaction of vortices as they are being convected downstream. So we call that kind of a regime unbiased flow regime. Look at the mass transfer characteristic of these regimes. So for a single body regime, we can find that the concentration lamps are actually convected in similar manner as the vortices. So we can actually say the mode of mass transfer here is convection because we have concentration lamps that maps directly on the saturation point of the vortices. And we actually find a very good symmetric. If we look at the time average scalar concentration, we find a very symmetric wake that is symmetric in both upper and lower side of the computational domain of the structure, I mean. So there is no meaningful average velocity in the downstream, which actually makes sense because as the lamps are convected downstream, we expect them to interact more with the free stream stream, which actually dilutes their concentration significantly. So for this one, we can conclude that the change in scalar pattern due to the size of structure is not so much, is actually negligible. So we don't have really a lot of changes due to the size of this, that is the structure. So let's go to the flow structures. And the flow structures, we find that there is actually a single vortex street downstream, and that single vortex streak resembles that of the isolated cylinder, but we have a difference in that we have base bleeding. If you look at the wake is not really attached to the cylinders, and that effect is actually known as the wake bleeding. So the wake is just symmetrical for all configuration, and if you examine the Stroud number, you find actually that as you increase the number of cylinders, then the Stroud numbers reduces. So that is actually an interesting finding. That is because as you increase the number of cylinders, huge vortices are shed that are more energetic but at a much lower frequency. So the Stroud number will actually reduce as you increase the number of cylinders in the domain. And similarly for the coefficient of drag. So this is actually just the pressure component. The friction component does not really is not really that significant. As you can see, it is about 20% of the total drag. So if we focus just on the pressure drag, we find that As you increase the number of cylinders in the domain, the drag also increases. And one more finding is that as you move from the outside deeper into the configuration, the dragging experiences by the member also reduces. So in fact, flow structures, we can say they don't depend really on so qualitatively they don't depend on the number of cylinders in the configuration, but for the forces they actually do. And the more the number of cylinders in the configuration, the higher the drag forces that they experience, and the deeper you move into the configuration, the deeper the more the drag force that you are going to experience. For the Shaud number, you find that the Shaud number that is experienced in this regime is always lower than that of an isolated cylinder, which is 5.6 for this regime, for isolated cylinder at this Reynolds number. So let's go to the asymmetrical based flow regime at gap ratio of 1.5. And for this case, we find that we have a very high interaction between vortices of neighboring cylinders. And instead of the convection that was dominant in the single body flow regime, now we have entrainment at the edge of the wake. So we have a lot of entrainment at the edge of the wake, as you can see in the instantaneous vortices. And then the mass transfer is pretty poor. So in the previous regime, we found that we didn't have a lot of concentration downstream, far downstream, but here actually we have a lot of concentration even far downstream, meaning that the mass transfer is actually poor, which is actually as a result of entrainment as opposed to convection. The other thing we notice is that the convection, so the transport is not really parallel to the streamwise flow. We actually have a wake that is at a specific angle to the. So if we look at the symmetrical based flow regime at the gap ratio of 2, now we find that the wake is no longer deflected toward one side, but is deflected towards both sides equally. So if you look at this figure here for both instantaneous as well as the time average scalar concentration, you find that the middle cylinder has a wide wake, and both of them are deflected almost equally toward the lower and the upper side of the domain. So this one is actually called asymmetrical based flow regime because the wakes are deflected equally towards either side of the structure. So the mass transfer characteristic, at the flow structures of this regime, these two regimes, and we find that for asymmetric based flow, as we have discussed, we have one that has a wide wake and another one and one side that have a smaller wake. So for the side by side cylinders, we have the upper part actually have a wide wake, but the lower cylinder has actually a pretty smaller wake, and that goes for all the members of configuration. You find that you have one side that it has larger wakes and another side that have smaller wakes. So we have a deflected wake. For symmetric based flow regime, as you can see in the second column, we have both cylinders in the configuration for two side by side cylinders having almost equal wake, but both of them deflected towards the outer cylinder. And actually that goes even for side by side cylinder having now a very wide wake in the middle because it is deflected equally toward the upper and the lower side. And that is also true as you increase the number of cylinders in the configuration. One thing we also notice is that the phenomenon in the first phenomenon that we realized in the single body flow regime, that the drag coefficient, the drag increases as you increase the number of cylinders in the configuration, is also true for this regime. And we can also see also as you move deeper into the structure, then the drag also increases, which we also discussed in the single body flow regime. One thing that is actually different from the single body flow regime is that the Stroud number is no longer uniform for all configuration, and it is actually much higher than the Stroud number of a single cylinder. So the Stroud number is actually much higher. The reason being that now the inner shear area is actually developing and shading vortices, but there is a lot of interaction in the downstream. So we find a uniform wake downstream, but the frequency is actually high, like that one of a single cylinder. So the mass transfer coefficient, or the Shaud number, we find it is actually comparable to the single cylinder. We have 5.8 in most cases, 5.8, 5.9, and for the single cylinder is about 5.6. So we can say that the mass transfer coefficient is actually Finally, for the side-by-side cylinder, we have unbiased flow regime, and unbiased flow regime is actually having a very large separation such that the interaction between vortices of neighboring cylinder is very minimal. So as we can see that the scalar concentration are transported almost parallel to the flow, pretty much parallel to the flow, and actually we can see that there is really minimal interaction between the scalar between the scalar from different sides. So you can see even far downstream we can tell which vortex was shared by which cylinder. Okay, and that phenomenon actually is consistent as you increase the number of cylinders in the configuration. So let's add the forces and the other flow structures. So we find that the forces are actually still high. They still maintain the same pattern of higher number of cylinders having larger drag force, and that means that obstruction is still there. We don't have a complete decoupling yet, and some people think that actually you won't have a complete decoupling until about S over D ratio of about 7.9. So we still have minimal interaction. That is why the forces are actually a little bit higher than that of a single cylinder. But on the other hand, the Choud number really resembles that of a single cylinder. We have it about 5.6 for all members in the cylinder, which means that insofar as mass transfer is concerned, we are almost fully decoupled because the mass transfer decouples before the flow structures. So a single vortex street is actually observed behind every member for at this flow region. So let's actually the inline cylinders and see how they fare on. So for the inline cylinders, so if we look at a small gap ratio, now we have a different phenomenon. In side-by-side cylinder, we have them behaving as the same as a single body, but a single body that is actually a little bit like elongated. So for this one, we have the same phenomena, but in different direction. So if you have a gap ratio of 1.05, the body behaves like an extended body. So the shear layer from the inlines from the upstream cylinder encrosses the the downstream cylinder, making it behave like an elongated body. And you find that the effect of the number of cylinder is now significant. As you increase the number of cylinders, then you find that the flow become more stable, shed the vortices much slower, and finally, actually, when this number of cylinder is 4, we find that we have a really stationary flow. We don't have any vortex shading going on. So if we increase the gap ratio to 1.5, then we have reattachment. So the shear layer from the upstream cylinder reattaches onto the surface of the downstream cylinder. So it no longer behaves like an extended flow, an extended body, but we have a cavity-like flow in between the cylinder, and that goes for all as we increase the number of cylinders in the configuration. But as we increase the number of cylinders in the configuration, the vortex shading behind the rear cylinder actually becomes less frequent and finally stops. When we have 3 and 4 cylinders, we find that we actually don't have any vortex shading, any noticeable vortex shading downstream. So we find that the effect of adding number of cylinders is actually stabilizing for this low this low gap ratio flow region. And another noticeable feature is that vortex shading is only occurs behind the trailing cylinder. So if we look at the gap ratio of about 4, as we increase the gap ratio, we find that now we have a shear layer that is attaching momentarily onto the surface of the other cylinder. So we have a shear layer that goes and attaches the other cylinder, but is momentarily disrupted because there is a noticeable development of vortices from the upstream cylinder. In most cases, we find that the vortices from the upstream cylinder, they develop, but they don't shade. They strike the downstream cylinder before they shade. But as we increase the number of cylinders in the configuration, we find that the vortices from the upstream cylinder act like they are washing away the vortices from the downstream cylinder, preventing them from fully developing. And that goes as we increase even the number of cylinders even further. And if we increase the gap ratio even further, then we have the core shading regime, in which all the cylinders in the configuration shade shade vortices. And we find that in this regime, the only effect of the upstream cylinder on the downstream cylinder is that the downstream cylinder behaves like it is behave like it is in the periodic flow, such that is being impinged by the vortices from the upstream cylinder, hence shading more energetic vortices. But apart from that, it behaves like an isolated cylinder. Okay. So let's look at the flow characteristic for these ones. And as we can see here, if we look at the flow characteristic, the drag coefficient and the Stroud number, we find that the Stroud number for all the members in the group are the same, and that goes without saying because we have only one vortex shading which is behind the rear cylinder. But actually the lift coefficient, the lift force is pretty much negligible in this flow regime for extended body flow regime. Finally, we see that the first cylinder or the leading cylinder experiences the highest drag, not as high as the isolated cylinder though, but it experiences the highest drag. And the second cylinder actually experiences negative drag. This is not a weird finding, it was found a little bit earlier. And this is attributed to the fact that the inner cylinder, the trailing cylinder actually sits right in between the shear layer of the upstream cylinder. So that makes it have a negative drag due to pressure stuff. Anyway, so let's see what happens really as we increase the number of cylinders. We saw that the streamlined become closed. We have a closed wake here. So for the first 2x side cylinder, we can actually see that we have a vortex shading. But as we increase the number of cylinders, we find that that actually now diminishes. And actually by the time we have 4 cylinders, we have a closed wake. We don't no longer have vortex shading. We have a closed wake, like the case of Rollin's number. And the time average contours of streamwise velocity shows that we have also a close to it behind the trailing sphere. So the mass transfer coefficient also behaves the same. We have the extended body. We have actually very high mass transfer from the leading cylinder, but actually as you move along but as you go downstream, you find that the mass transfer is not as great. This is because actually we have very minimal mass transfer from the trailing cylinder. So let's increase now the gap ratio to about 2, and we find out in the reattachment flow regime. Now in the reattachment flow regime, we don't really have stationary flow in between the cylinder, but we have the flow behaving like a cavity flow. In between the cylinder, we have a cavity kind of a flow. And we see that even for this case, as we increase the number of cylinders, the wake stabilizes and we have a closed wake. And similar for the similar phenomenon is observed for the trailing cylinder. We have a closed wake from the number of cylinder equals from n equals to 3 to n equals to 5. And that is actually the same phenomena. So the coefficient of drag still behaves the same. We have the leading cylinder having the highest drag, and then we find the second cylinder actually have negative drag, and then drag increases as we go along. One of the noticeable features insofar as mass transfer is concerned in this regime is that we have significantly higher mass transfer coefficient of the leading cylinder from that of an isolated cylinder. So that's something to notice. And also you can notice that as you move downstream, the mass transfer coefficient diminishes. So as you move downstream, the mass transfer coefficient diminishes in this region. All right. So this is the mass transfer. Structure for this regime, and actually we find that it is similar to the flow structure. So we have really not much to discuss here, as we have said that the leading edge, the mass transfer coefficient is much higher than that of the isolated cylinder, and also we find that the structures are actually similar to the vortices, the flow. If we increase the gap ratio to 4, now we have now a disrupted or the bistable flow regime. Now in this flow regime, we have the vortices forming from the upstream cylinder forming, but those vortices, they don't shed. They strike the downstream cylinder before they shed. Hence, they mix with the vortices from the downstream cylinder and shed still as one thing. So in most of the cases, you will find that we don't have noticeable shading from the upstream cylinder, but we have actually noticeable shading from the downstream cylinder. And that goes as you increase the number of cylinders in the domain. But now, one of the phenomena that actually emanate in this one, instead of stabilizing the flow which was happening at lower gap ratio, now the instability starts from the downstream cylinder and moves up. So you find that the trailing cylinder are shading, they are co-shading, but actually the upstream cylinder are not shading, they are still actually in what is called the reattachment regime, or the reattachment regime, or in the disrupted regime. So all the cylinders don't behave the same. So the gap between the cylinders, the flow in between the gap between the cylinder is actually different for different configuration, and this is actually the phenomenon that happens at as you increase the number of cylinder. And similar thing is observed for the mass ratio. We find that the mass ratio really follows the structure of the flow, and we find that the mass ratio, as you increase the number of cylinders, the mass transfer coefficients also increases, something that we didn't notice in the other flow regimes. So we find that for the leading cylinder, for two cylinder we have about 5.79, and that one increases as you increase the number of cylinder in the configuration. The other things that actually happens is that this is actually opposite to the reattachment regime, is that from the second cylinder, as you move downstream, the mass transfer coefficient actually increases, while the other side it was actually decreasing. But the same thing happens insofar as Stroud number is concerned, because we have this all the members in the structure having the same Stroud number. The reason is because they have one vortex shading frequency, since the vortices from the upstream cylinder comes and actually force the vortices from the downstream cylinders to shade, forming one large vortex. So that is actually in this flow regime. And for the flow structures, we have actually discussed that. So for the flow structures in the co-shading regime, if we go to the co-shading regime, for the flow structures, we find that all the cylinders in the configuration are actually now shading. Find that in this regime, all the structure, all the cylinder are shading the vortices, and the effect of the upstream cylinder on the downstream cylinder is that the vortices from the upstream cylinders impinges on the vortices on the surface of the downstream cylinder. Actually, that causes the vortices from the down cylinders to shade prematurely, but all the members now have the same vortex shading frequency. As you can see, the Stroud number is the same for all the members, and we can find that the coefficient of drag is now comparable to that of an isolated cylinder, at least for the leading cylinder. But for the other cylinders, the drag is still lower, as the instability starts from the lower side, from the trailing edge, as you approach the leading edge. For the mass transfer, we have the same thing actually, but we can see in this regime that the mass transfer for the leading cylinder is pretty close to that of an isolated cylinder. We have about 5, we have about 6. And actually, the other thing we notice is that we really don't have a specific format in which it behaves. The Stroud number behaves as you move along, and that is because we have shading that actually happening from all the cylinders. So we don't have a very good relationship for mass transfer as we move down the cylinder, down. And that is it for the. So in conclusion, we can say that we have 4 flow regimes for side-by-side cylinders for a gap ratio of 1.05 to 4 at Reynolds number 90 at least. And those flow regimes, as that for lower regimes, we have the single body flow regime, and then as you increase, you have a deflected wake toward one side, which we call a symmetric burst flow regime. Then we have symmetrical burst flow regime, where we have both we have deflection on both sides with equal angles, and finally we have what we call an independent regime, in where we have all the cylinders behaving independently. Finally, we can say that the drag force increases as the number of cylinder in the configuration increases, and this is true for all the gap ratios. And also we saw that as we move deeper into the structure, the drag force also increases. So the drag force increase experienced by members at different position is actually different depending on the size of the structures. Another thing we noticed is that the lift force is always positive, downward and outward pointed. That means that two neighboring cylinder always experience a repulsive force, which is something that we can say for all gap ratios and all configuration of different members. Insofar as mass transfer is concerned, we say so that most cylinders in the configuration and low gap ratio exhibit Shell number that is lower than that of isolated cylinder, and that is not really the case for higher gap ratio, because at that regime all the cylinders have about similar mass transfer coefficient, which is comparable to that of isolated cylinder. For inline cylinder, on the other hand, different flow patterns are realized depending on the number of cylinders in the configuration. So we find that in for very low gap ratio, we have extended actually goes to reattachment regime as you increase the gap ratio, and finally we have co-shading regime if the gap ratio is really big. So vortices from the upstream cylinders on impinges on the surface of the downstream cylinder, causing them to shade. So in this regime, all the cylinders experience the same Strahl number, and then the leading cylinder is always having the highest mass transfer coefficient or the Strahl number. So that is it for this talk, ladies and gentlemen. That's it. Thank you so much.